In previous section, we learned about chemical processes, which are also known as chemical reactions. And we learned that chemical reactions are those processes in which elements and compounds react with each other to form a new compound. Now, forming a new compound is the key element of a chemical reaction. In a chemical reaction, existing bonds are broken and new bonds will be formed. Now, because all elements and compounds and atoms and bonds are so small, we can't really see them. So how do we know that if a chemical reaction is taking place or not? So the answer is that we don't actually look for the bonds being formed. We look for some other evidences or other indications of a chemical reaction or a chemical change. So during a chemical reaction, we may observe a change in the color, uh, and we may see a formation of a solid. For example, a yellow solid is formed when we are mixing these two liquids. Um and we may observe a heat being produced. For example, a firework, there's a heat, or maybe a evolution of a gas, it may bubble also, or we may notice a aroma. So all of these observations or all of these um properties, they are indication of a chemical reaction or a chemical change. So these are evidences of a chemical reaction. Millions of chemical reactions occur every second in a biological cell. These reactions are known as biochemical reactions or metabolism. Biochemical reactions produce the compound and energy necessary for living and making it possible for us to breathe, grow, and reproduce. So in this section, we will consider the quantitative relationships between compounds and elements in a chemical reaction, and it is known as writing and balancing a chemical equation. As I mentioned earlier, millions of chemical reactions take place every second in a living organism, and these chemical reactions are known as metabolism. So in metabolism, chemical compounds present in food, they break down, and in breaking down they form waste material. Waste material is also a new compound, and in this process energy is released. uh, so this energy which is produced in these biochemical processes are needed for all kind of biological functions such as speech, breathing, growth, and reproduction. So when a chemical reaction happens between two different chemicals, we may observe evolution of gas bubbles, we may see color change, we may see uh, solid form, or many other evidences may be there. But what actually happens at the atomic or molecular level? So how do molecules behave when the atoms or molecules of one substance are reacting with the other substance? So atoms, ions, and molecules in any matter, as we know, are in constant motion. So when they are moving, for example, if I have a container, and in this container I mix two different chemicals. One is green and one is blue. They are constantly moving in all direction as shown here. So oxygen and nitrogen gas are there and they are constantly moving randomly. And when they are moving, they collide with each other as well as with the walls. Okay. So all these collisions are random and there are millions of collisions every second. So they collide with each other, they collide with walls, and they collide with similar molecules also. So these collisions are all random. During majority of these collisions, these particles collide and simply bounce off from one another. Occasionally, however, the collision has enough energy, so the collision is strong collision, so they have enough force that when they collide, the existing bonds break and new bonds will form. and that collision will result in formation of a new product as shown here. So in this example, oxygen molecules are colliding with nitrogen molecules. Most of these collisions will not result in anything, but some of the collisions will have enough energy or enough force so that the existing bonds between oxygen and nitrogen atoms will break and they will form new bonds, and resulting new molecule will be NO, which is nitrogen monoxide. So this entire chemical change can be represented with the help of an equation, and this equation is known as reaction equation or chemical reaction. So reaction equation will have reactants on left hand side. So for example, in this case, our reactants are nitrogen gas as well as the oxygen gas. This G represents that these molecules are gas molecules. And then on the right hand side, we have product or products. In this example, we have only one product, but in some other reactions, we may have multiple products. Although reactants and products are totally different compounds, however, they are made up of same atoms. For example, the product is made up of nitrogen atom and oxygen atom. A good analogy is for a chemical reaction, we may consider that a reaction is like a set of Legos. All we do in a chemical reaction is that we mix and match the Legos in such a way that a new design is created. But the starting number of Legos and the ending number of Legos has to be the same. So that's a good analogy. So for example, if we have set of two red Legos and two yellow Legos, so you can see these are different designs or different molecules, but after they react, new designs are formed or new molecules are formed, but they are made up of same Legos which we started with. So in a chemical reaction, only bonds between the atoms change. Atoms do not change. We do not lose any atom and we do not gain any atom. We just, the bonds between those atoms are changed. So therefore, we can say that reactants and products are although different from each other, but they contain the same atoms. So a fundamental principle that applies to all chemical reaction is that atoms are neither created nor destroyed, and this is known as law of conservation of mass. So law of conservation of mass states that in all chemical reactions, atoms are neither created nor destroyed. An example of a law of conservation of mass is shown here. For example, if we have sodium sulfate solution here and a calcium chloride solution inside here, and together if they weigh 300.23 grams, now if we mix these two solutions by shaking them up, after mixing, a chemical reaction will take place and new substance, calcium sulfate, which is a white precipitate powder, and NaCl will form, but the mass will remain exactly the same what we started with. So that is a proof that in a chemical reaction, atoms are neither created nor destroyed. So what's happening in this reaction is calcium chloride is reacting with sodium sulfate, and the end product is calcium sulfate plus sodium chloride. The meaning of this 2 we will learn in few slides later. So this 2 is needed to balance the equation. So in this reaction, if the starting mass was 300.23 grams, the end mass of the product will also be 300.23 grams. And the mass is same because we have same number of atoms. We just shuffle them around to make a new compound, but we did not lose any atom, or we did not gain any atom. That's why mass did not change. A chemical reaction is described by a chemical equation. For example, if we have a container or a chamber, and in this chamber we have nitrogen gas molecules, and we have oxygen gas molecules, and these molecules are moving and they are colliding with each other, and after collision they are forming a new molecule, and that new molecule is NO. So this is a chemical reaction taking place in that container. But how do we express this chemical reaction? So the expression of this chemical reaction is known as chemical equation. So chemical equation will identify the reactants and products as well as their relative proportions, and some other relevant information is also given in the equation. So for example, their physical states, whether they are solids, liquids or gas. It will be shown many times. If our reactants are dissolved in water, we use the symbol AQ. AQ stands for aqueous. Aqueous means they are dissolved in water. The reactants and products are separated by a plus sign. Plus sign means that they are together. For example, in this reaction chamber, nitrogen and oxygen are reacting with each other together. So that's why we show this plus sign. Reactants are on the left hand side of the equation. Products are on the right hand side, and they are separated by arrow. So remember, that's important. It has to be an arrow, not equal sign. So if you put equal sign, that would be wrong. And then whole number coefficient indicates their relative proportions. For example, this 2 means that in this chemical reaction, 2 NO molecules are produced. So this number in front of the reactants or products, these are called coefficient, and it represents how many molecules of that particular species are being formed. So this 2 indicates that in this particular reaction, 2 nitrogen monoxide molecules will be produced. If there is no number, for example, here in front of nitrogen and oxygen, there is no number. So then it is understood that it's 1. So if there is nothing there, that means it's 1. So how do we read this chemical equation? The way to read this is we say 1 nitrogen molecule reacts with or combines with another single oxygen molecule to produce 2 molecules of nitrogen monoxide. Now, why it's so? So let me explain in a little bit detail. So imagine that purple sphere represents nitrogen atom. So this is nitrogen, this is nitrogen. So that would indicate the N2. So N2. So this would be N2. Right. So let me show a bond. So this would be nitrogen and nitrogen. And imagine that the red is oxygen. So this is oxygen atom, that's oxygen atom. So in this collision, what will happen is that first the bond between the nitrogen will break and bond between the oxygen will break. So one of the nitrogen atom combines with one oxygen to form a NO. So these two. So the other one will combine to form the other one. See, remember the Legos? We don't lose any atom. So it will form the other NO. So that's why we have, for every 1 nitrogen and 1 oxygen, we have 2 of these. So these coefficients are important because they are necessary to show that law of conservation of mass is followed. Consider this chemical reaction, and let's try to answer these questions. So first question is, identify the reactants and products. We know that reactants are given on the left hand side of the equation. So therefore reactants are, we have two reactants. So these two are reactants, and the products are carbon dioxide and water. So these two are products. Second is identify the coefficient and explain what they signify in terms of molar ratio. So coefficient, so in front of the first reactant, the coefficient is 1, and then so it means 1, this molecule, the name of this molecule is propane. So 1 propane, and the coefficient for in front of oxygen is 5. So it means 1 propane combines with 5 oxygen molecules. That's what it's signifying. And once 1 propane and 5 oxygen combine, they give 3 carbon dioxide molecules and 4, so coefficient for water is 4, so 4 water molecules. So in terms of ratio is, the ratio between the reactants is 1:5, because 1 propane needs 5 oxygen, and the ratio of molar ratio of products is 3:4. So 3 of carbon dioxide and 4 water molecules will form. And next part is identify the physical state of each reactants and products. These small letters in parentheses represent the physical state, and they all have G. G stands for gas, so they are all are gases. And finally, how many carbon, hydrogen, and oxygen atoms are on each side of the arrow? That's very interesting. So let's write the equation one more time. So C3H8 plus 5O2, and on this side of arrow we have 3CO2 plus 4H2O. Okay, the coefficient, whatever it's in front, it represents how many of these molecules are there. This 5 coefficient means that we have 5 O2s, right? And so therefore if I count the atoms, each O2 has 2 atoms, right? So 5 of this will be 2 here, 2 here, 2 here, 2 here, 2 here. So total atoms of oxygen will be 10. So that's the meaning of this coefficient 5. Um, so 5 means that we have 5 O2. Each O2 has 2 oxygen atoms. So 5 of them together will be 10 oxygen atoms. Similarly, C3, this 3 means we have 3 carbon atoms. And this 8 means we have 8 hydrogen atoms. Okay. So in the reactant side, we have 3 carbons, 8 hydrogens, and 10 oxygens. Let's see how many we have in the product side. Again, this 3 represent we have 3 CO2s. It means 1, 2, and 3 CO2s. And 4 water means that we have 4 water molecules, 3 and 4. And if we count, we have how many oxygens? 1 here. So we have 1 oxygen here, 2 here, 3 here, and 4 here, and O2. So 5, 6, 7, 8, 9, 10. So total oxygens are 10 oxygen atoms. Similarly, if we count the carbon atoms, so we have 1 carbon, 2 carbon, and 3 carbon. So we can say we have 3 carbon atoms. And if we count hydrogens, you can see 2 hydrogens, 4 hydrogens, 6 hydrogens, and 8 hydrogens. And so we have 8 hydrogen atoms. Interesting thing you will see is that the total number of carbons in the reactant is exactly same as total number of carbons in the product. So what does it mean, or what do they indicate? They indicate that the law of conservation of mass is valid, or in other words, we do not lose or gain any atoms in a chemical reaction. Only new bonds are formed, but we don't lose or gain any atom. The total number of atoms before the reaction and after the reaction remain the same. According to the law of conservation of mass, the total number of each atom type on the reactant side of a chemical equation must be equal to the total number of atom type on the product side of the equation. A chemical equation that displays the lowest whole number ratio of coefficients such that there is equal number of each type of atoms on both sides is known as a balanced chemical equation. For example, we know that hydrogen gas reacts with oxygen gas and it will form water molecule. Now, if we think about it, this is the reactant side and this is the product side. Now, let's count the atoms. On the reactant side, we have two hydrogen atoms as we have H2, and similarly, we have two oxygen atoms. Now, in the product side, we have two hydrogen atoms, but we have only one oxygen atom. Now, something does not add up here. So in this equation, we are losing one oxygen atom. So this equation is not a correct representation of a chemical reaction, because chemical reactions must follow the law of conservation of mass. So this kind of equation is known as unbalanced equation. So before we uh, write any chemical reaction, we must know how to balance this equation. So we now need to understand the process by which we can balance an equation. But before we do that, just understand what's the meaning of unbalanced equation. In unbalanced equation, the total number of atoms on the reactant side will not be equal to the atom in the product side. Or in other words, it does not obey the law of conservation of mass, because according to that law, atoms should not be created or should not be destroyed. So hence, this is not the correct representation yet. So let's learn how to balance an equation. So before we learn how to balance a chemical equation, let's take a look at an example of a chemical equation which is already balanced. So this equation is the combustion reaction of methane. So methane is the gas which we use as a fuel in ovens or even in the lab. Formula of methane is CH4, and in this reaction, one CH4 molecule reacts with two oxygen molecules and it produces one carbon dioxide and two water molecules. These are the coefficients and they are used to balance the equation. So now if we think about it, so in CH4 we have one carbon atom, so the black sphere represents carbon atom, and four hydrogen atom. Each white sphere represents hydrogen atom. We have two oxygen molecules, so each red sphere represents oxygen. So total we have four oxygen atoms, right? So in the product, if you count, we have again 1, 2, 3, and 4 oxygen atoms. So exactly the same. One carbon in the reactant side, the black sphere, only one carbon in the product side. Four hydrogens in the reactant side, and again if you count, we have 1, 2, 3, and 4 hydrogens. So this is an example in which the total number of different types of atom in reactant side is exactly same as total number of each type of atoms in the product side. Okay, so let's learn how to balance a chemical equation. So in a chemical equation, we have reactants. For example, in this case, we have these two reactants and we have products. Products are on the right side of the arrow. So we have these two products. And in front of each reactant and a product, there will be coefficient. Now, coefficient could be any number, any whole number. It could be either 1, 2, 3, 4, and 5. And we need to find these coefficients. Okay. There are general guidelines to determine the coefficient. Even if you don't know any method, you can just guess a number and see if it works, and eventually you will come up with a combination which will work. That's called hit and trial method, but that may take forever. So if we follow these guidelines, you will be able to find these coefficients in a much smaller amount of time. So the rules are: first is balance one atom at a time. For example, if you want to balance carbon atom, so just balance the carbon atom. Balancing means that the total number of carbon atoms in the reactant side must be equal to total number of carbon in the product side. And the second is start with an atom which is found in only one compound. For example, carbon is found only in one compound in the reactant side and only in one compound of the product side, right? Oxygen is not a good candidate because although oxygen is only in one compound in the reactant side, but it's present in both of them in the product side. So don't start with oxygen. So start with a compound or an atom which is found only in one of the compound in both reactant and product side. So you can either start with carbon or hydrogen, both will work. So in this example, we're going to start with carbon. Another tip I would like to give you is that if uh, any element or let me see, pure element is present. Pure element means one type of atom. For example, in this case, oxygen is pure element because it's made up of only oxygen. So balance that atom at the end. That's extremely good tip. So in other words, in this equation, because oxygen is pure element, so we will balance it at the end. You don't have to follow it exactly, but if you do, it will make your life much more easy. Okay, so we're gonna start with carbon and we're gonna end with oxygen. So that's our game plan. So let's start with carbon first. Balancing means that we need to equalize the number of atoms. So in the reactant side, we have 6 carbon atoms in the reactant side. And if we look at the product side, only 1 in the product side. So one thing which we cannot do is we cannot put a subscript here. You cannot put C6 right here and say it's balanced. No, that is incorrect. Only thing we can do is we can put any number here. These are called coefficient. Any number, whichever number works, you can put it. Okay, so any number. And whatever number you put, that number will be multiplied by to all the atoms in front within that molecule. So because we have 6 carbon atoms, so therefore we must put 6 here, right? So now we have 6 on this side and 6. So this is 6 times 1, so that's also 6. So now our carbon is balanced. Okay, so now we are done with the carbon. Okay, so as we have balanced carbon atom and we have said that we're gonna balance oxygen at the end, so that means that now we have to balance hydrogen. So in the reactant side we have 14 hydrogens and in product side we have only 2. In order to make this 2 to be 14, so we need to multiply 2 with 7. So it means that now we need to put 7 here, because whatever we put here, so that number will be multiplied to the entire molecule, right? So 2 were already there, so we put 7 here, so 7 times 2 is 14. So therefore, the coefficient in front of water should be 7. And now we have balanced hydrogen atoms. Only thing left is oxygen. So let's see how to balance oxygens now. Okay, so in this equation, our carbon is balanced, 6 carbon here, 6 carbons here. Our hydrogen is balanced, so 14 hydrogens here. So 7 times 2 is 14 hydrogen here. Only remaining atom is oxygen. So in the reactant side, we have 2 oxygen atoms. And in the product side, we have 6 multiplied by 2. So that 6 times 2 is 12 here. And 7 times 1, we have 7 times 1 or 7 here. So 12 plus 7 in the product side, we have total 19 oxygen atoms. Okay. Okay, so now that's a tricky situation. Now, why this is tricky? Because now we need to get reactant side to be equal to 19, right? So only way I can get 19 here if I multiply this side by 19 by 2. Right? So 19 by 2 multiplied by 2, because there is already 2 here. So whatever number is here, that number has to be multiplied by this coefficient. So when we multiply, these two cancel and we will get 19. So that will give 19 on the reactant side and total 19 on the product side. So that will work. Okay, so therefore we can put 19 by 2 here. Yeah. Okay, so we're gonna put 19 by 2 in front of oxygen to balance it. Now, technically, this equation is balanced, but there is a problem. The problem is, according to the rules, the coefficients have to be a whole number. Right? So 7 is okay, 6 is okay, and 1 is okay, but 19 by 2 is not okay because it's a fraction. And in a balanced equation, we cannot have a fraction. Okay, so in order to remove the fraction, what we need to do is we need to get rid of 2. So the simplest way to remove this is we will multiply the entire equation coefficients by 2. So what does that mean? That means this 2 will be multiplied to this coefficient, this coefficient, this coefficient, and this coefficient. Why we multiplied by 2? Because we want to get rid of this 2. This 2 is 19 by 2. When we multiply, the 2 and 2 will cancel. Okay, so when we multiply it, so this equation will become 2C6H14 plus 2 times 19 by 2 O2, 2 times 6 CO2 plus 2 times 7 H2O. This 2 and this 2 cancel, so the equation will be 2C6H14 plus 19O2, and in the product side 6 times 2 is 12 CO2 and 7 times 2 is 14 H2O. And now we have a balanced equation. So once you have a balanced equation, so always make a check. Always check if your number of atoms are equal or not. So let's verify it. So how many total carbon are there? So 2 times 6 is 12 carbons. How many hydrogens? So 2 times 14, that would be 28 hydrogen. And how many oxygen? 19 times 2, that's 38 uh, oxygen atom. Now let's compare the product side. So in product side, so 12 times 1, so that would be 12 carbon, so that is okay. So 12 and 12 equal, so this is good. And how many hydrogens? So 14 multiplied by 2, that's 28. So 28 is also good. And finally oxygen will be 12 times 2 plus 14 times 1. So 12 times 2 plus 14 times 1, this also comes out to be 18. So hence this equation is balanced, and that's how we balance any chemical equation. Okay, so let's practice this problem. In this problem, we have to balance similar looking equation. Again, in this case, we're gonna start balancing carbon first. So in the reactant side, we have 6 carbons, and in product side, we have 1 carbon. So therefore, in order to balance it, so we need to put 6 here. So now carbons are balanced. Now, as I said, if there is any pure element present, leave it till the end. So oxygen is the pure element, so we're gonna balance oxygen till the end. So carbon is balanced, so only other atom present is hydrogen. So we have 12 hydrogens in the reactant side and only 2 hydrogens here. So therefore, in order to make this 2 to be 12, so we will multiply this also by 6. Right? Okay, so 6 times 2 is 12. So now hydrogens are also balanced. Finally, let's balance oxygen. So oxygen, we have 2 oxygens here and 2 oxygens here. So total is 4 oxygens. And in the product side, we have 6 times 2, that would be 12. And 6 times 1, that would be 6. So 12 plus 6, 18 oxygen atoms. So now we need to make it also 18. So the way to make it 18 is we already have, so 2 here. In order to make 18, so we need 16 here, right? So 2 is here, so that's why we will multiply 8 here. So 8 multiplied by 2 will be 16, and 2 here, that will be also be 18. So now our equation is balanced. So let me clean this equation up. Okay, so if we count the carbon atoms in the reactant side, so carbon atoms is 6, and in the product side, carbon atoms are 6. That's balanced. In the reactant side, hydrogens are 12. In the reactant side, hydrogens are 6 times 2. 6 times 2 equals 12. So that's also good. And in the reactant side, oxygens are 2 times 1 plus 8 times 2. That comes out to be 18. And in the product side, oxygens are 6 times 2 plus 6 times 1. That is also 18. So every atom is balanced. From the balanced chemical equation, it is possible to calculate the maximum number of moles of a product that can be formed from a given number of moles of reactant. This means that we can also calculate the mass of the product formed given the mass of the reactant. And this is known as stoichiometry calculations. Let me explain the concept behind stoichiometric calculation using the example of a sandwich. So we can consider making a sandwich like a chemical reaction. In order to make one sandwich, imagine we need 3 slices of bread, 2 slices of turkey, and 4 strips of bacon. And then combination of all of these components will give us a sandwich. Right? So we can say that 3 bread, B for bread, plus 2 turkey, plus 4 BC is bacon, gives us one sandwich. So this would be our equation to make the sandwich. It's a balanced equation, imagine. So now using this equation, we can calculate that if we start with any reactant, how much product can be obtained. For example, if instead of 2 turkeys, what if I have 4 turkey sandwich or 4 turkey slices, right? And I have, let's say, enough of bread and enough of bacon. So from the equation, I can calculate the mole ratio or the ratio. So 2 turkeys give me 1 sandwich provided I have enough bacon and enough bread. So I'm going to ignore the other 2 components. So if 2 turkey slices give me 1 sandwich, so 4 turkey should give me 2 sandwiches. All right. So what if I have 20 turkey slices? So if 2 are giving me 1 sandwich, so 20 will give me 10 sandwiches. So this is called the ratio between reactants and products. So from the quantity of reactants, we can calculate how much product can be obtained. And that's the stoichiometry calculation in really simple terms. So let me expand this a little bit more. So now imagine that if I have uh, 12 breads, 12 bread slices. Again, I'm only going to consider the bread, and I'm going to imagine that I have enough of turkey and enough of bacon. So I'm not going to consider that. So from the balance equation to make the sandwich, I know that 3 bread slices give me 1 sandwich. So 3 bread slices give me 1 sandwich. So that's the relationship, and I can use this relationship as a conversion factor also. So now if I have 12 breads, how many sandwiches can I use? So I can use this as a conversion factor, right? So it would be 3 bread down here and 1 sandwich here. So it will cancel. So that will give me, so 3 and 12, 4 sandwiches. So from 12 breads, I can technically get 4 sandwiches, provided I have enough turkey and enough bacon. And this is the meaning of stoichiometric calculation. In stoichiometric calculation, instead of bread and turkey and bacon, we have actual chemical compound, but the process is exactly the same. Let's now apply the stoichiometric calculation concept which we learned from this sandwich example to a real chemical reaction. So a balance equation is given to us. In this equation, ethanol is reacting with oxygen to give us carbon dioxide and water. And in the balance equation, we have 1 ethanol mole. So all these coefficients are moles. So that's why they are called mole to mole stoichiometry. So from the equation, we can say that 1 mole of ethanol reacts with 3 moles of oxygen to form 2 moles of carbon dioxide and 3 moles of water. So a balance equation gives us the mole to mole conversion or mole to mole relationship between any reactant any product. So for example, if I can say that 1 mole ethanol gives me how many moles of water? My answer is it gives me 3 mole water, because you can see that ethanol in a balance equation, we have 1 mole here and we have 3 mole water. And in this case, we are ignoring the other two. The concept is that once you establish the mole to mole conversion between reactants and product, you can pick any two and you can directly relate to them. So for example, in this case, I'm picking ethanol and water. And what's the mole to mole relationship between ethanol and water? So from the equation, I can see the relationship is 1 mole of ethanol is giving me 3 moles of water. And we can use this relationship as a conversion factor to calculate the amount of product obtained, which we will discuss in next slide. Now let's see how do we apply the mole to mole relationship between reactants and products to calculate the amount of any other substance. For example, you may see a problem that how many moles of oxygen are needed to react with 5 moles of ethanol, and the balance equation is already given to us. So in the problem, we are trying to find the moles of oxygen, and we are given with moles of ethanol. So given 5 mole ethanol and find number of moles of oxygen, right? So it means we need to now relate ethanol and oxygen. So we go back to the balance equation and we see from the balance equation what is the mole to mole relationship between the ethanol and oxygen. So if we look carefully, the coefficient in front of ethanol, so this is ethanol, is 1, and coefficient in front of oxygen is 3. So the mole to mole relationship between ethanol and oxygen is 1:3. And why we are using ethanol and oxygen? Because that's what we need. The problem asks us to find oxygen from ethanol. So that's why we are considering these two and we are ignoring the other. We don't need to look at what's happening with the other. Okay, so now the relationship is that 1 mole ethanol is giving us or needs 3 mole oxygen. So that's the relationship. From this relationship, we can write the conversion factor, and that's same as earlier conversion factor. So that's left hand side over right or right over left. So there we will get 2 conversion factors. So one will be 1 mole ethanol on top and oxygen at the bottom. So 3 mole oxygen, or the second is when the oxygen is on the numerator and ethanol is in the denominator. So next step is use dimensional analysis. So whatever is given, so given is we want to go from mole of ethanol to mole oxygen. That's what we want to. So that's the given and that's the find. So always start with given, multiply with the conversion factor, and you get your answer. So how many moles are given? We are given with 5 moles of ethanol. Now, which conversion factor to use? We're gonna use the conversion factor where the mole ethanol is in the bottom. So therefore, we're gonna use this conversion factor. So 1 mole ethanol, and on top will be 3 mole oxygen. Mole ethanol cancels with mole ethanol, and the answer is 5 times 3, 15 mole oxygen. So in other words, we found that if we have 5 moles of ethanol, we would need 15 moles of oxygen to react with it. And this is the stoichiometric calculation problem. Let's try another problem. In this case, how many moles of carbon dioxide are produced from the reaction of 5 moles of ethanol? Again, balanced equation is given, so we can find the mole to mole relationship. And let's first write given. So what is given to us? So given to us, again, we have 5 moles of ethanol. And what do we want to find? We want to find number of moles of carbon dioxide, right? So therefore, we need to know the relationship between ethanol and carbon dioxide. So ethanol is here in the balance equation and carbon dioxide is here. So coefficient in front of ethanol is 1 and coefficient in front of carbon dioxide is 2. So therefore, the relationship is 1 mole ethanol is equal to 2 mole CO2. CO2 is carbon dioxide and C2H6O is ethanol. Okay, so we know that from the relationship we can find write 2 conversion factors. So one conversion factor will be 1 mole ethanol over 2 mole CO2, or the other one will be 2 mole CO2 divided by 1 mole ethanol. Okay, so now apply the dimensional analysis. Okay, so we will start from the given, multiply with the conversion factor, and we will go and find the value of CO2. So given is 5 mole ethanol. So which conversion factor we need to use? We're going to need to use the one where the ethanol part is in the bottom. So therefore, we will use this conversion factor. So this will be used. So down here will be 1 mole ethanol and up will be 2 mole CO2 So mole ethanol cancels with mole ethanol, and when you multiply, the answer will come out to be 5 times 2 is 10 moles of CO2. So this is how we can find the moles of product if the moles of reactants are given to us. And the conversion from the mole of reactant to mole of product is known as stoichiometric calculation. In previous stoichiometric problems, moles of reactants were given and we found the moles of products. So this section is the stoichiometric calculation, and we found the conversion factor from the coefficients from balance equation. Now, what if instead of moles of reactant, we are given with mass of any reactant? Then what to do? The concept does not change. In the beginning of this chapter, we learned how to convert mass of any compound into moles. So this problem now begins with the conversion of mass to moles. So once you know how to convert mass to moles, and as soon as you convert mass to moles, then you can apply the stoichiometric calculation, and you can convert the moles to moles of product, and then moles of product can also be converted to mass of product B, because we know how to convert moles to mass. So these kind of problems are known as mass to mass stoichiometric calculation, because you start with the mass of a reactant and you end with the mass of a product. So the steps for mass to mass stoichiometry is, first you convert mass of a given to moles of the substance using the molar mass concept, and then you convert moles of the reactant to moles of the product B, applying the stoichiometry concept which we learned in previous slide, and then finally convert the moles of B into mass of B, again using the molar mass concept. So let me explain this by using an example. You may see problems similar to this one. What mass of nitrogen is produced when 130 grams of sodium azide decomposes in an airbag? So now again we have a balanced chemical equation, and from the balanced equation we can see 2 moles of sodium azide will give us 3 moles of nitrogen. But we don't want mole to mole now. We have a grams of sodium azide and we want to know the mass of nitrogen. So this is mass to mass conversion. It's not mole to mole conversion, right? So therefore step number 1 is convert mass to mole, right? How do we convert mass to moles? We did that earlier in the beginning of this chapter by applying the concept of molar mass. So sodium azide, the molar mass of sodium azide is 23 from sodium times 3 times, and each nitrogen is 14. So that's equals to 23 plus 42. So that's 55 grams per mole. Okay, so the molar mass of sodium azide is 55. Okay, so what's the meaning of 55 molar mass? It means that 1 mole sodium azide equals 55 grams. So that's the moles to gram. So we can use this to convert mass to moles, right? So that's a relationship number, let's call this number 1. So once you know how to convert mass of Na and 3 or sodium azide to moles, now next step is you convert moles of Na and 3 to mole of your product N2. So here we're gonna need a concept in which the moles of sodium azide are related to moles of nitrogen, and that comes from the balance equation. So if we look at the balance equation, coefficient in front of sodium azide is 2 and coefficient in front of nitrogen is 3. So therefore we can say that 2 moles of Na and 3 is equal to 3 mole of nitrogen. So that's the mole to mole relationship. So number one was mole to mass relationship between sodium azide and mass, and number two is mole to mole relationship between moles of sodium azide and moles of nitrogen. Okay, so let me just write this cleanly. So we start with the mass of sodium azide, and then we convert the mass to moles of sodium azide, and we're gonna need a conversion factor here. And after you convert mass of sodium azide to moles of sodium azide, then we're gonna need to convert moles of sodium azide to moles of nitrogen. Why? Because that's what we want to find, nitrogen, right? So again, we're gonna need a conversion factor here, and finally we're gonna convert moles of nitrogen to mass of nitrogen. So here we're gonna again need a conversion factor, and that conversion factor comes from molar mass of nitrogen, and conversion factor 1 will come from molar mass of sodium azide, and the middle one, mole to mole, that's gonna come from the balance equation or stoichiometry calculation, right? Okay, so we already have conversion factor 1, that's going to be from equation 1. We already know the relationship between the moles of sodium azide and moles of nitrogen, that's equation number 2. Finally, we're going to need the relationship between moles of nitrogen to mass of nitrogen. So the molar mass of nitrogen is 28, because N2, 2 nitrogen, so that's 28 grams per mole. So that means that's the molar mass, right? So therefore the relationship is 1 mole nitrogen is equals to 28 grams. So that's the third equation or third relationship. Now we have everything we need for this calculation. So let's plug in the value. So what is the mass of sodium azide given to us? It is 130 grams multiplied by conversion factor. So now this conversion factor is between mass of sodium azide and moles of sodium azide. So this is gonna come from the relationship between the mass of azide and moles, right? So therefore it will be 55 grams down here, and up here will be 1 mole sodium azide. So grams cancels with grams. Now we have mole of sodium azide. So next is we need to convert moles of sodium azide to, so we are here, right? So next step is moles of sodium azide to mole of nitrogen. So we're gonna need a conversion factor between moles and moles. So that's gonna be from equation number 2. So this part. So because moles of sodium azide is on top, so therefore 2 moles, so from here, right? So 2 moles sodium azide, and up here will be 3 mole nitrogen. So now in this case, moles of sodium azide cancel with moles of sodium azide. Now we have moles of nitrogen. So we are at this step. Next step is moles of nitrogen needs to be converted to mass of nitrogen. So we're gonna need a conversion factor between moles nitrogen to mass nitrogen, and that's gonna come from equation number 3. So multiplied by, so that's where it's gonna come from. So down here will be 1 mole nitrogen, this part, and up here will be 28 grams. So again, mole nitrogen cancel with mole nitrogen. Now we have grams of nitrogen. I'm leaving this as grams. Actually, this is grams of nitrogen. This is grams of sodium azide. You should write whose grams are you talking about. and 130 is grams of sodium azide. It's understood, I just left that, but you should write it. So let's write the leftover numbers here. So we get 130 multiplied by 1 multiplied by 3 multiplied by 28 grams of nitrogen divided by 55 times 2 times 1. Okay, so let's multiply the numbers in the upper half of the equation. So that would be 130 times 1 times 3 times 28. So I got 10,920 divided by 55 times 2, that will be 110 grams of nitrogen. And when I divide it, so my answer is 99.27. Well, only 2 sig figs are needed because our number is given in 2 sig figs. So 99 grams of nitrogen. So if 130 grams of sodium azide decomposes, we get 99 grams of nitrogen. So this is the mass to mass stoichiometry calculation, in which we start with the mass of the reactant and we find the mass of the product at the end.